Hello everybody. In this video we'll be covering one of the sections in chapter 7 of our textbook entitled Chemical Reactions. In this video we're going to be discussing precipitation reactions. So in our previous video we learned that many reactions are done by mixing aqueous solutions of electrolytes together. When this is done, often a reaction will take place from the cations and anions in the two solutions, essentially exchanging with one another. If the ion exchange results in forming a compound that is insoluble in water, it will come out of the solution as a precipitate, and that's what this picture is here. There's an actual cloud of solid forming when we mix these two liquids together. So let's consider here this reaction between potassium iodide and lead nitrate. It's going to form potassium nitrate, which is aqueous, so that means that it is soluble, and it's going to form this lead iodide that is a solid, and therefore it's going to precipitate out of reaction. We can kind of picture this as happening in two steps. The first step, we have our potassium iodide and we have our lead nitrate. Then we mix them together and we have a solution that has all of our ions in it together. After that, the iodine anions and the lead cations are going to find each other inside of the solution. And they're going to form together to make lead iodide, which is insoluble, and it's going to start to form a solid at the bottom of the container. In practice, when we mix them together, these two steps happen so fast that it appears as if there's no intermediate, that it's just almost an immediate reaction to get your precipitate out. A lot of precipitation reactions happen that way, although sometimes they are slow enough that you can kind of picture this happening. You mix them together and then they slowly start to form this precipitate. So in practice, this is what it looks like when we mix these two together. You can see that the second that it touches the liquid, it starts to form that lead iodide. But conceptually, we know that this is actually a two-step process. If we consider the reaction between potassium iodide and sodium chloride, we form two soluble compounds, potassium chloride and sodium iodide. In this situation, when we mix the two liquids together, we don't get any precipitate forming. So let's discuss a process for predicting the products of a precipitation reaction. This is going to bring together a lot of the skills that we've been working on so far. First, we're going to write the formula for the reactants and determine what ions each aqueous reactant has. Then we'll exchange the ions. Okay, so the cations from one reaction with the anions from the other one. Then we're going to balance the charges that the ions have to get the formula of each product. Then we're going to balance the equation. Then we'll determine the solubility of each product in water, and we're going to use the solubility rules for that. And if a product is insoluble or only slightly soluble, it's going to form a precipitate. If neither product will precipitate, then we're going to say that there's not going to be any reaction. So let's do a little example here. When an aqueous solution of sodium carbonate is added to an aqueous solution of copper 2 chloride, a white solid forms. First, we're going to write the formula for the reactants and determine the ions present when each reactant dissociates. So we had our sodium carbonate, that's this guy right here, and we have our copper 2 chloride, that's this guy right here. Don't forget that carbonate is one of our polyatomics. So when we think of sodium carbonate, we know that this is sodium ions bound to a carbonate ion, and copper chloride is copper bound to a chloride ion. Then we're going to exchange the ions. So what that means is that instead of sodium being associated with a carbonate, we're going to associate it with the chloride. And instead of copper being associated with the chloride, we're going to associate it with the carbonate. Then we're going to write the formulas of the products. Okay, so don't forget to cross the charges and reduce like I showed you before when we were writing ionic formulas. This is particularly important here because we wind up with sodium chloride. We don't have two sodiums over here. We now only have the one because these both have a positive 1 charge and a negative 1 charge. And the copper has a +2 charge. The carbonate has a -2 charge. So we wind up with a little bit of a different result there. Then we're going to balance the equation, and we can see that what we're going to need to do is add this 2 here in order to balance our sodium and chlorine atoms on this side of the equation. The next thing we need to decide is what is the solubility of these products. Okay, and we know from our solubility rules that carbonates tend to be insoluble, and this is not one of our exceptions to that rule, whereas sodium was. That's why it was aqueous in the first place. And so it's going to form a solid, which we're going to indicate with an S here, whereas sodium chloride, our table salt, we know that that one's soluble. So our final result is that when we mix these two together, there will be a reaction, and the precipitate that's going to come out is going to be copper carbonate. We can do a little practice here. What's going to happen when we mix potassium chloride and silver nitrate? When we exchange those ions, we find that we make potassium nitrate, which is going to be very soluble. Both potassium and nitrates are soluble. And we're going to make silver chloride. And we know that silver nitrate is the only soluble form of silver. So silver chloride is going to make a solid, and we're going to precipitate out silver chloride. We have sodium sulfide and calcium chloride. When we do these exchanges, we see that all of our products are going to also be soluble, and therefore we're not going to have any reaction. So we have a whole bunch of new equation types, some of which that I already showed you, for talking about precipitation reactions and ions in aqueous media, called ionic reactions. So these are equations that describe the chemicals put into the water and the product molecules. And when we do that, we call those molecular equations. So there's different kinds of ionic equations. We're first talking about molecular equations, and these are the ones that we've been talking about thus far. This would be an example of a molecular equation. Equations that describe the actual dissolved species are called complete ionic equations. Okay, so we know, for instance, that in an aqueous media, this guy does not exist as potassium nitrate, but as potassium ions and nitrate ions. So aqueous electrolytes are written as ions. This includes, again, our soluble salts, strong acids, and strong bases. And insoluble substances and non-electrolytes are written in their molecular form, just like they would appear up here. So magnesium hydroxide would stay the way that it is. These are going to be our solids, our liquids, our gases that are not dissolved. So an example of this exact same equation written in a complete ionic equation would be like this. Okay, we're breaking up each one of these into its ions. Remember that the coefficient goes with them, all right, each individual piece, and then we're writing them all out. But where we have something that isn't aqueous, we still write it in its molecular form. So to write a complete ionic equation, we're going to rewrite the molecular equation, but dissociate the strong electrolytes into individual ions. Strong electrolytes must be aqueous. Okay. All soluble ionic compounds are strong electrolytes. We'll remember that. Strong acids are our strong electrolytes. And molecular compounds do not have ions. We're going to leave them in their molecular form. So ions that are both reactants and products are called spectator ions. Let me show you what I mean. If we go back to that same equation, you can notice that our potassium ions appear on both sides of the equation. And so too do our nitrate ions. So if we think about what the physical meaning of that is when we write that, that basically means that nothing happened to these guys. They were spectators. They just watched magnesium and hydroxide combine together to form magnesium hydroxide solid. So when you have something that's on both the left-hand side and the right-hand side and nothing's changed about it, that means no reaction happened between them. So basically, to condense this down a little bit and talk and focus only on the thing that's actually happening, we have what we call the net ionic equation. And what that is we're going to remove these spectator ions that didn't really do anything and just write out the remaining bit of the equation. And now we've really gotten down to the heart of what's happening in that reaction. So to write a net ionic equation, we first identify the spectator ions in the complete ionic equation. Identical ions on both sides of the equation, that's going to be our spectator ions. And then we're going to cancel out the spectator ions. That's going to give us our net ionic equation. So in summary, a molecular equation is a chemical equation showing the complete neutral formulas for every compound in the reaction. A complete ionic equation is a chemical equation showing all the species as they are actually present in solution, meaning our electrolytes are going to appear as ions. And a net ionic equation is an equation showing only the species that actually participate in the reaction. Let's do a little practice. Let's write the ionic and net ionic equation for this guy right here. Give you a moment. So anywhere where I see aqueous, I'm decomposing it down into its ions. Okay. Remember that if we have two potassiums here, so this subscript becomes the coefficient in the complete ionic equation. We need to still represent that we have two potassiums here in order to get a balanced equation. Okay? Don't forget to balance these guys. Next, we'll need to identify the ions that appear on both sides. We have our potassium and our potassium. We have a nitrate and a nitrate. These guys combine together to make barium sulfate. So we'll remove those, and we get our net ionic equation. Let's try one more. We have sodium carbonate and HCl. That's going to sodium chloride, carbon dioxide, and liquid water. If we write out our net ionic equation, everywhere where we have aqueous, we're again decomposing this down into its ions. Basically the reverse of what we were doing before when we were writing the ionic formulas. We're remembering to keep our coefficients where necessary to keep our balance. Gases are going to be written in their molecular form. Liquids will be written in their molecular forms. We're only decomposing the aqueous ones. Then we go ahead and identify our spectator ions. So we have sodium and sodium, chloride and chloride, and we remove those to write our net ionic equation.